happy Tuesday, everybody. I think the recording will work today. We'll give it a shot. How'd the midterm go? Okay, no surprises, right? Hopefully we had a good enough review. It's just a checkpoint. It surprisingly goes badly for some people. But I mean, you folks are the ones coming, so generally if you come, it goes okay. It's the people who are like, oh, I'll watch the videos, and then like me, don't ever watch the videos for their online class, because they're like, I'll do it later. And they don't do so well. So this is sort of that checkpoint for that. We should be able to get those probably this week. I'll work on them. I got to get the project scores added. I know I was waiting for a couple people to enter your own self-assessments. And again, generally those are great. So if you're concerned about it, let me know. We can always meet and chat about them directly. But people are pretty good at letting me know how they did on those, which is cool. So I am thinking, not that people love writing things, but it'd be nice to get like a self-assessment before you see the solution and then a self-assessment after you see a solution. Because sometimes there's like, oh, I might have missed this thing, but that feels like a lot of extra work. So I'm hopeful that like I can find a way to make it valuable and not a waste of your time. So we'll see, because the goal of all of this, right, is that you do the labs for practice, you do the projects for more practice, a little more on your own, figuring things out to build up to this final project. And if you can get the final project done, then great. That was sort of the goal of everything. Yeah.
Project 3 is due next week, right?
Next week, yeah. So we're going to start. I want to give you the final project on Thursday, just so you've got like a full couple weeks to work, 4 weeks to work on it. If you don't start, that's okay, but at least let's like start thinking about it. And project 3 is not huge. It's not tons and tons of stuff going into it here, so hopefully you can get that one wrapped up. And if you did want to work with a partner for sort of like a trial run for project 3, go for it, because we do need to work with a partner for the group project, because that is one of our outcomes we're checking, is you can work in a team, right? Did I not find team in here? Did I do this wrong again? I really thought this one mentioned a team. Did it not? Okay. I think I'm confused between the two, because I thought the list was the same outcomes here. Well, we should work in a team. I guess it's not required. Interesting. I really thought it was on my list here. I did this last time, and I'm just confused again, I guess. So it's better if you work in a team, but I guess if you don't want to, then that's fine. Yeah, so we are nearing the end of our content. We're going to talk about stacks and queues this week. Goes relatively quick. You should be able to get through stack, no problem. Probably even get into queues, bless you. And then we'll finish up queues on Thursday. Next week, searching and sorting. Again, the easy ones here. We don't get into the advanced sort of sorting stuff. And then a little bit on files and streams, which is fantastic. Files and streams are great. And then a little talk on ethics, which is a very important topic you'll come back to again later. We sort of introduce the topic here. The last week I just have planned for group project work time. So for you to work with your partner on this, that way everyone's supposed to be here, or at least have the time set aside for it. Ideally you can get it done by the 18th, so you don't have anything to worry about for finals week. And then that's ideal. If not, that's okay. And then on 4/23 you just present. So everyone will take turns presenting their projects, showing, hey, this is it runs, show your output sort of thing. And then it might be a question or two about your code, and we'll go from there. So should be a lot of fun. I know 8 a.m. is awfully early. I'm not looking forward to that, but it's okay. They got to pack in 3 exams in a day, right? So it's the 3 slots. I won't even say that'll be fun, but it goes pretty well. So we're just presenting. That's a good practice to do as you work in industry. You'll present, here's what you're working on to your working group, that sort of thing. So it's nice to present to your classmates. So questions, thoughts, concerns, we okay? They're scheduled to the end here? Okay, very cool. Let me pull up Visual Studio here. We're going to look at stacks and queues. They are lots of fun. And again, we have built-in ones, right, in the library we can use, but we're going to spend a little bit of time looking at how we might build these ourselves, so that we can better appreciate why they're fast at what they're fast at. That's sort of the goal here. Make a new project. This is week 12. Week 12 already, my goodness. Make sure I find the right one here. This is week 12, stacks and queues. Excuse me. All right. And we add a new file here, a new little header file. Make this one for our stack. We'll make a little class for stack. Now, that's probably zoomed in enough, right? Are the lights good? You need them? Okay. So things we do with the stack then. We'll come back to the private section here in a minute, but looking at public functions, right? This idea, what is that abstract way that we interact with a stack? So regardless of how we create a stack, what do people do with a stack? And then this is a template class here, right? We have a stack of some type. Just like we make a vector of some type, this will be my template, type name t here. So this will be a, isn't that template? Oh goodness, what am I doing wrong here? I have to go copy paste from our other template stuff.
It might have been template and then in between the arrows type name T.
That's right.
With the last
There, thank you. Yes.
with the last thing that we did, because we had to have two template type name T's, it ended up not working to me because it didn't like me saying type name T a second time within the within the class, not outside of the class.
Okay.
So I was messing around with it, talking with a friend who's not in programming, and I'm like, I can't figure this out. I was trying to do it before we could like play games or something. He was like, what if you just change it to a different letter? I went, that wouldn't work.
Yeah, you
right?
could-
And then I
Yeah,
changed
you
it to
can
a
have
different letter, and it did.
Yeah, if you're doing like a pair, you have
Right.
two different, yep. Yeah, so tracking which letter is which is a little bit obnoxious here. And sometimes I feel bad, but T is pretty well accepted here when we're doing templates. This is the T, the type here. Yeah, so if you do different like keys and values, K and V or other things like
It
that.
does have to be a single character, though. It can't be like type name and then a string of characters.
I think it can be something long. Yeah,
Oh, okay, gotcha.
yeah, so, yeah, so it's just another name we assign here
Right, yeah.
for this, yep. So things we do with a stack, right? And it works just like a stack of anything that you think of, right? Now we'll call it push. I guess you don't push things on top of a stack in the real world. You put something on, but you push things onto a stack. So we're going to say this is just a void function for push here. And it takes a t item. So whatever we're going to push onto the stack here, right? We'll push something on. And we'll come back to actually how we do that in a minute here. You can get the t thing that's on top. They call this peek here. So you peek, see what's on top of the stack. So you push, you peek, and then you pop. You can actually remove that item then from the stack. Whatever's on top of the stack, you pop it off. I didn't name these things, but sure. So you can push an item, you can peek and see what's on top, you can pop an item off. These are our common operations here. And when we think about how fast things should go, right, we want these to be quick. So we want these to be constant time operations here. And we can get constant time pretty easily, right? At least on average. We'll look at ways we can speed that up if we really want to for all the time here. But to see what's on top of the stack should be constant. That should be immediate all the time, right? We shouldn't have to go and sort anything. We shouldn't have to go look for anything. It's just whatever's on top of our stack here. And then to remove that item, again, we want to get constant time here. We don't want it to be slow. We don't want to have to do any counting here. So the quick, easy way for us to do this is to use a vector. Right? Vectors work pretty well for us here. So if we have a private vector of type T, this is our items, right, or something. They go include vector, and using our namespace standard. Okay, so if we just have a vector of items here, then we should be able to put something into the vector, take something out of the vector. Works pretty well for us here. Now, removing things is a little bit obnoxious, right? Vectors aren't so good at that, right? It takes a little bit of extra work here, but we could, right? We could just, when you go to put something in, we add it to our vector, so we'll need a quick little constructor here. So we'll make our stack constructor, and then all we need to do is initialize items, make sure items we can start adding stuff to, right? And really it's ready to go. Right? We don't even need to do anything super fancy here. So if we want to push something, we take our items, we just push back. Because item is a type T, we can add it to our vector of type T. It just fits. So peeking, then what is on top of the stack here is the last item in the vector. So we can return our items at, and then the last item here should be at items.size -1. Okay, that's the last index. And then popping, we have to remove from the vector. This one gets a little bit more obnoxious here. And honestly, I just have to go Google it because I don't remember. Vector remove item. Oh, look at that. It's gonna, how do we erase an item from a vector by index? Erase. Don't want the beginning, we want the last one. So we can use beginning plus an index, okay. Advanced an iterator, erase, okay. We got some options. So we're going to need to get the same item, right, before we erase it. So we have our T item here, is what's at the end here, and then we want to go get rid of it, right? So we'll take our vector, or our items, we're going to erase, and what do we want to erase? We want to erase the last item here, so that's our vector dot, that's the, is it the end? Nope, not our items. Dot, I think it's the end will give us the last item here, but the last one doesn't actually like exist, right? So I think we want -1 to go back one. Right, because end is the end where there's nothing left. It's not actually the last item when we've played with our iterators before. So if we go back by 1, I think that'll ought to do it here. So you take beginning plus the index. We'll probably do it here. Let's see. Should we try it? Okay, so let's go do something with our stack here. So let's include our stack. Let's make a stack of type, well, an integer is probably pretty easy here. So we'll have some numbers, and we'll take our numbers, and we should be able to push like 1. Now, stacks, right? There's ways that you describe stacks and queues. With a stack, it's a first in, last out. The first thing that goes in is on the bottom of the stack, so it's the last thing that's going to come out. Or you might say it's the last in, first out. The last thing that goes into the stack is the first thing that comes out of the stack. So we've actually worked with stacks because when you call functions, they go onto the call stack, right? And we said, okay, C++ remembers, hey, I was here at this line, and then I called a function. Now I'm at this function at this line. And when you call another function for that function, it goes onto the call stack, right? So they work in order of the stack. And when it's done, it comes off the stack. We go back to the function we were at before. So we've worked with it. It just, never really wrote our own stack for it. So we're writing our own. So if I push 1, 2, 3, 4, when I pull them off, I should get 4, 3, 2, 1. Because the last thing that went on is the first thing that's going to come off, right? You don't usually want to take something out of order of the stack because it will probably fall over, right? It's sure. Now, stack might also do something like tell me when it's empty or not, right? So we might have a Boolean for is empty. That might be kind of useful, so we can return the items.size equals 0. If our size is 0, we're empty. If it's not 0, we're not empty. That's a pretty quick one here. So we could say while numbers dot is empty, numbers is empty, and not is empty. Like, while we're not empty, we can see out my numbers dot pop. Right. We'll take the item as long as we're not empty, pop it off, and print it. Sure. So if it works, we should get 4, 3, 2, 1. Uh-oh, we got some build errors. What do they do? Really? Said there were build errors. There it is. Pop must return a value. Thank you. So you're going to return the item. This one might actually be void because you might have to peek first, but I like when it returns. It makes life easier. Hey, 4, 3, 2, 1. So I think our erase seems to be probably working, right? Because it's grabbing the top item each time. So it seems to be removing it for us with the vector. So if we look at performance-wise here, adding something on average is going to be constant because we're using a vector, right? The worst case, remember when we use vectors, eventually things have to resize. We've talked about that with this array-based storage. So we don't have always O of 1 performance. We don't always have constant time, but on average it's constant, which is pretty good, but we could do better, right? Remember when we looked at our linked lists, it's always constant time to add, no matter what, because there's never any resizing. So if we wanted to use a linked list behind the scenes for storage, we will always get constant time here, right? Which is probably better, right? What about for popping something off? Is this always going to be constant time, or does it need to do some sort of resizing? But eventually, they'll probably resizes once, like if we add 1,000 items and then we take away almost all of them, we don't want to keep 1,000 memory addresses, locations in memory here. We should resize down so we're being more efficient. So eventually we'll resize. So this is another O of N operation, worst case. Now, most of the time, though, it's not going to resize. It's fine to just take the last thing off. This one works pretty quick. So on average, it's here. But we could increase this, right? So if we used a linked list behind the scenes, we can get faster storage for all of these things, or faster operations for all these things in the worst case performance, which is kind of cool, right? So if we think about if we're going to be adding and removing a lot of things, that averages do add up, right? So when we think about performance, this is average time. Here, average time. Oh, this will always be O of 1, right? Just to look at the last item. No matter how many n we have, we can always get the last one. But on average here, with the array, the vector-based, array-based storage, we only get average times. So if we wanted to change this to use our linked list, we could get better performance. Excuse me. Now, it's a bit of a thought exercise, not super really worth a lot of our time at the moment here. Is it okay if we skip that, or do you want to see it with a linked list? Okay, so you could, right? Should we just leave a note? We'll leave a note here. So using linked list would give worst case O of 1, right? So that would be one thing we could do to make this faster with a stack here. Now, it might seem silly to use a stack when behind the scenes it's just a vector. Like we could just use this vector in our program over here and do that. So why do we want to use a stack? Well, sometimes you want to limit what people can do with your items, with the way that you're holding data. So if the way that we need to write our program is that people can't interact with things other than what's at the top of the stack, we can give them a stack because there is no actual way to interact with anything other than what's at the top of the stack. So if it fits that use case, right? If we want to encapsulate all those details together into what we're writing to solve our problem here and say we don't want people to have access to things other than the top of the stack, we can use a stack. So it puts limitations on what people can do with our objects, with our data. So if that fits our problem that we're solving, that's great, right? Now, it'd be nice if we could say, oh, we know people will do the right thing, and we know if we give them a vector, they just won't access the other indexes, but you don't really want to trust people to do the right thing, right? If we can enforce it in code to protect the integrity of our object, we're going to do that. That's one of the reasons we write our classes with our private attributes and our public functions, right? We want to protect the integrity of our class. We want to make sure bad stuff doesn't happen to our object, to our classes. So if this is one of the ways we can protect it, it fits really well. Now, not everything is going to use a stack, right? But we could use stacks for things. And if you wanted to solve that Towers of Hanoi puzzle without using recursion, you could use a stack, right? I think we look at the two different ways of solving it. I think we just Googled it, right? So you can use the stack to remember the things you're supposed to do, right? Without having to use recursion, because all recursion does is put those on the call stack. So now C++ is making a stack and tracking all that stuff for us. He said, okay, well, I don't know how to move 5, but I know how to move 4. When I'm done moving 4, I'll come back and move the 5th disk. Right? We put it on the call stack, and then C++ just managed it. So we could use a stack itself to do all the movements with the Towers of Hanoi and not have to do recursion, which is technically a little bit less efficient, right? Because we have to be tracking all those variables. Every time you call the function, it has to track all the different arguments you gave it. So it uses a little bit more memory. But it was super easy to write. Was it like 6 lines of code or something to write with recursion? Without recursion, it was a bunch more. So it caused a little bit of trouble for us. But stacks are a lot of fun, and we use them all the time because that's a core functionality of how code runs. When it gets to a function, it just puts that on the call stack because it needs to know where to come back when it's done. So stacks are a lot of fun. But that's about all we're going to do with our stack. This one is not the most interesting. It's kind of a boring data structure, but it goes pretty well, right? So a queue is a little bit more interesting. Should we work on a queue? Yeah, you guys are so excited. I love it. Sorry, it's early. So now with a queue here is another template class, a template of type name T here. We'll have our class for queue. We've got some private attributes, and we'll have some public functions here. Now a queue, if you are British, you know is a line, right? We don't often use that word here in America. I don't know why. It's such a good word here. But what letters are silent in Q? Is it just the ending UE or all the UEs are silent? 4 silent letters? Just the letter Q?
Well, you can spell Q just Q-U-E without the second U-E.
That's a Q ball, right?
Yeah.
In
Or no, Q ball
Bill-
is
Bill-
C-U-E, I think.
Is it really?
Yeah.
Oh my goodness, English is awful. A terrible language.
I've seen Q-U-E though, for Q4. I think.
QUE. The meaning here. Here's our dictionary. Is it Q, Q, or Q? Let's see. What is it here? Looks like Q is supposed to be
They have a whole article about
what the
people looking up Q.
phonetic spelling. It's CUE. So it looks like Q is supposed to be UE.
So it's just so commonly spelled wrong that it's considered an actual word.
Apparently. But Q is an abbreviation for Quebec? Oh, QUE is, I don't know. Okay. This is not helpful. Why is this not helpful? Look, we're getting ads for U of M Dearborn.
Yeah.
That's funny. I'm on their website often enough. They've tracked it. Anyway, so our Q. So things that you do with the Q. You can NQ an item, add it to the queue. You can see what's at the front of the queue, and you can DQ, or take the front item off. And just some fancy terms here. So we have a void for NQ, a T item. You can get the front item here, and you can DQ, take the front item off. So these are ways we interact with our queue. Okay. So to add an item here, now again, we could use a vector here behind the scenes, and we'll talk about performance for this one here. So let's do our include vector, and using our namespace. Oh my goodness. Using our namespace. So if we have a vector of type T for our items here, to add something to the queue, it adds to the back. Right? When you get in line, you get in the back of the line. That works out pretty well. So items dot push back our item. That one goes pretty well. The front here then, we're just going to return items at index 0. The front of the line, like the first thing in the line. So when you talk about these things, it's the first in, first out, or last in, last out. Usually people say first. So first in, first out, versus our stack, which was first in, last out. Right? The stack, the first thing that went in is the last thing to come out. With the queue, the first one that goes in is the first one to come out, because it's a line here. And then to DQ, we need to remove that item at the front here. Now, to get the item at the front here, that's always O of 1, because thanks to our vector, right? That's super quick here. To add an item, again, on average, it's O of 1. This is average time. Here, O of 1. And to DQ that item, then, if it's using a vector, how many operations does it take to remove something at the front of a vector? Or an array-based list, or like array-based storage. Remember, that's n operations, because everything has to shift back to fill that gap. You can't have gaps here. So this one is terribly slow. This is an O of n operation, which we say is slow and bad.
By front, you mean specifically the first one? That's
Yeah,
within-
yep, items at 0.
Yeah.
Yep, because that's one we want to remove. So this one is no good here, because we'd have to remove that one. So we'll take our T for the item, is my items at 0. And then we want to erase, so items.erase the items.beginning here. And this is where it gets really slow. So removing this one means everything else has to shift. Slow here. Because you can't have nothing at index 0. Right? So what was in index 1 has to move to index 0. What was in index 2 has to move to index 1. Right? It's on and on and on. So n items have to fill that empty spot here. So this one is really slow. So this is no good, right? This just doesn't work well with the vector at all. Versus our stack was like, oh, sure, it's fine. Its average case is still good. Here, we know it's a little slow. So using the linked-based storage here is way faster right off the bat here. right, to use our linked lists. Because removing something in a linked list is slow to get to that index. But if we're removing the front thing, we just know where it is, right? It's just really easy. Now, there's a trick we could use if we wanted here to make this a little faster here. So we'll look at what the trick is first, and then we'll say, oh, we know it's easier using a linked list. But if you wanted to make this faster because you really like vectors, or like we didn't know that linked lists existed, right? We have an option here. We could have a integer for the front index. So if we have an int for the front index here, we can track where the front is then. So we'll say, we'll make a little q constructor. We'll say my front index is 0. And every time we remove something then, or the front item here will be at the front index. So it starts off at 0 to look at the first thing. Every time we dequeue something, we're going to take the thing at the front index, and instead of erasing, we just don't do anything with it. And we'll take our front index plus plus. We'll just say, okay, sure, I'll just move where I'm tracking the front here. So if I add 5 things, 1, 2, 3, 4, 5, and I want to dequeue the first one, we'll just say, okay, let's just pretend like that one's not there. Let's remove it. Just count passes. So the next time you want to dequeue something, we'll see what the front index is. We'll see what the front index is. We'll see what the front index is. So this one now is constant time. It's really fast because you can get at things by index like that, remember? With our arrays, with our vectors, super fast by indexes. Now, what's going to happen though is eventually if you add and remove and add and remove and add and remove, our vector just gets bigger and bigger and bigger and bigger and bigger and bigger and bigger. Right? So we're trading faster performance for using more memory. So it's a trade-off here. So we get constant time operations here. Saying a vector gives fast performance for using more memory. Right? Because our vector just will never get smaller. And that one feels a little bad, right? To say, oh, we're just going to increase in size forever. This is when we say, hey, there's probably going to be a memory leak. Right? We're just going to use more and more and more memory. Now, it's not really the same as like using dynamic memory and not deallocating it, but we're asking for more memory every time the vector gets bigger, and we're never giving it up. So it's still essentially a memory leak. Right? Same thing here. So this is not great with this kind of queue here. Now, we can make it faster, though, or a little bit more memory efficient with some quick arithmetic, right? So that quick arithmetic is going to be, well, if I don't care where those values were at the front, like once I'm done with it, right, let me draw a picture here, and hopefully it doesn't crash my stream. We'll see. I'll go back and look. So let's assume our vector has a bunch of spaces here, right? Because remember, vectors are a little bit oversized to start. I don't know, we'll put a couple in here. So we'll add some numbers. We just do the numbers in order. So let's add a 1, a 2, a 3, and a 4. And then let's dequeue a couple. We'll take them off. So let's say, okay, let me get the 1 and the 2. Right? So I know my front index is right here, right now. Right? That's my 3. And we'll add some more numbers. We'll add a 5, and a 6, and a 7. Now I've got some empty spaces over here, right, at the front. So instead of just pushing back every time, what if we say, hey, let's just use that empty space? So when I go and add an 8, instead of resizing my vector, what if I put it right here? So I'm going to track, hey, this is the back of the vector, or the back of the queue. This is the front of the queue. And then, okay, let's pop a couple, or dequeue a couple. Let's take the 3 and the 4 out here. We'll say, okay, now the front is over here. I've got a couple more spaces. I can add a 9 and a 10. And maybe I want to dequeue a couple more. So let's get the 5, the 6, the 7. Let's even take the 8 here. So the back of my queue is over here. The front of my queue is over here. Right? This is a circular queue. We want to be efficient with our memory usage, with our storage here, so we can just store things in a circle. Right? This is actually much more memory efficient, and we still get really good performance out of it because we're using that empty space. Once we take the numbers out, we can use that space. And that's actually some quick arithmetic, which is nice. So let's do, we're going to change this then for the back index here. And we'll say our back index 0. Every time we NQ something, we don't want to just push back now. Right? So this gets to be a little bit tricky. We have to manage the size of our vector here. Or we could even use a fixed array. So instead of using a vector of type T, we could just use a T array here of items. Right? And we could do some dynamic memory. This gets to be a little bit tricky here to do it that way. That's probably the nicer way to do it here. So we'll pretend like we're going to do all the work here. Is that okay if we just kind of leave it as a thought exercise? So if we were to have this T of items here then, right, we could go and size it to a certain size. So we can say my items equals a new T of size. I don't know, we'll do like 10 to start. So we're going to have 10 spaces to start here. Right? Then we go to add something, we're not going to push back, we're going to take our items at the back index and assign it to the item. Or assign the item to that location. And then we'll take our back index plus plus. But now we need to see what if I reach the end of my 10 items here, I want to circle back to the front. Right? So then I can take my back index modulus equals the size. So I need to know what my current size is. So I probably need another int for current size. So we'll say current size equals 10, and we can use that variable then, right? Which is nice. Modulus the current size. So if I was at 10 and I increased my index, or so if I was at 9, right, which is the last item here, and I increased to 10, 10 mod 10 puts me back at 0. Right? I circle back around to the front, which is good. That's where I want to be. Right? The only thing now I have to check is to see what do I need to resize my storage. Right? What if I ran out of 10 spots? Right? If the back of my queue hit the front. Right? So if I keep on adding items here, so we added a bunch of items, and then we said the back is here, and we keep adding an 11, 12, 13, 14. Right? The back just keeps moving and moving and moving, and we circle back to the front here. We add a 15, and then the back moves again. If the back equals the front, we're out of space. Right? So eventually we have to resize. So if the back index is equal to the front index, we'll resize. Right? And we have to write a little function for resize. So that'd probably be a private function. Void resize. And this is, we've done this thing before here, right? So make bigger array and move everything. Reset back and front index, right? So we just copy everything. Start at the front index, move them to the new array that's bigger, and then reassign my items to the new array, right? We've done this before. So this is the exercise here. Now, our average performance then is going to be constant still, because eventually we have to resize. So it still takes some additional time here, right? So again, using a linked list where we can just infinitely add things for constant time is better. But if you really like arrays, you can use an array for it. Right? Before we had linked lists, you didn't know any better. Right? We had to manage all this ourselves. We had to resize things ourselves. And then we're like, hey, here's a linked list where you don't ever need to resize. And everyone was really excited, right? Because not having to do all that work of resizing is pretty nice. Right? The downside then is you can't get at things at given indexes. But for a queue, do we care if you can't get at things in the middle? No, it doesn't matter at all, because the queue says you can touch the front thing and you can add to the back. That's literally the only things you can do with a queue. So not being able to access the things in the middle quickly, no one cares, right? So using a linked list to store a queue is even better for us, right? So this whole exercise of making this circular queue, it's cute, and it's a fun little thought exercise, but it's not efficient. Right? So using the linked list is going to be better for us than using this circular queue anyway. Right? And we did a whole bunch of extra work here that we didn't really need to do. So I'm kind of skipping over the cliff notes. Usually we write the bad way and then we look at it, and that just seems terribly dull to write it badly on purpose. We kind of did that the first time. Right? So with our stacks and our queues, we have a limited set of instructions, a limited way you can access it. Right? That API, the way we interact with it abstractly, is very limited. With the stack, you can push and you can peek and you can pop. With the queue, you can NQ, you can look at the front, and you can DQ, and that was all. Right? But they're really quick, especially if we use linked lists to store them. They're really quick all the time. Using the vectors are fine, or using arrays are fine. You can get good performance out of it if you do a little bit of work. Pretty good performance here. And they're not too bad to write. But again, we would just use the ones in the standard template library. Right? We would not write our own. You don't need to, right? It's just the exercise of writing it and thinking about how we do these things is useful for these sorts of things. It feels really silly to show these, I'm sorry, to be like, and then just use the ones out of the standard template library.
You want us to use the ones out of the standard?
Yes, yeah, don't use your own. Okay. I mean, you're welcome to use your own if you want for the project. I don't recommend it, right? And so just use the standard template library ones. What you don't want to do is use a vector and just try not to do the bad thing of taking things to the wrong indexes. You could, but the whole goal is, can we limit ourselves to these functions, the push, the pop, and the peek,
Yeah.
and then the front NQ, DQ, right? That was the sort of the idea here. We need the is empty in here as well. We'd have to track that sort of thing. So we can make these work, right, that way. We got through all the stacks and queues already? My goodness. Really thought we'd have more. Okay, so I don't actually have a whole lot more to talk about with stacks and queues. Then again, building them ourselves is just an exercise. Right? Using it, if it fits your problem definition, it's fantastic. Right? We want to give people limited access because people will do dumb things. So if you give them more access than they should have, they could do dumb things and hurt themselves. Right? So some limited access is pretty good. So why don't we'll save Thursday for some work time on the project, and we'll talk about the final project on Thursday. I'll have that all defined, ready for you to go. Again, if you want to start on it, great. If you want to wait on it, that's okay too. But then you'll have all of April to work on that. So probably the 3 weeks or so. Searching and sorting will go relatively quick again. So I think we'll have a little bit of time each Tuesday, Thursday to work on this group project together with your partner if you want. Should be a lot of fun. And streams will probably take most of Tuesday, but ethics won't take all of Thursday for sure. That's a relatively quick talk. And then we'll have work time for that. So we are nearing the end, believe it or not. Just a couple new topics, last little couple things. And we are almost through CIS 200. It's been a lot of fun. If you got questions, let me know. Always happy to chat. And if not, I will see you for lab. We will play with stacks and queues and just doing some silly exercises just to get comfortable using those functions. Right? And again, just like anything else, you can make the template type of another template type of another template type of another template type, like we did with our standard template library. Right? So you can have queues of stacks of anything, right? You just keep on nesting all those braces here, and it gets to be lots of fun. All right, that's all I got. You folks have a great Tuesday. I'll see you later.